This lab demonstrated Newton's second law, or the momentum principle. I dropped a ball from my back deck and then used Tracker to extract the position versus time data. In this lab, the net force acting on the ball was something other than zero, and we created two computational models to account for the two different possible scenarios, one of the ball in freefall and one accounting for turbulent drag also. Because the net force on the ball was not zero, the ball was accelerating as it fell towards the earth. I used a basketball as the object whose motion I analyzed in Tracker. The forces acting on the object were the force of gravity, which was obtained by multiplying the mass of the ball, which was 0.45 kilograms, times the gravitational constant for Earth, 9.8 meters per second squared. There also was a turbulent drag force, which is directly proportional to the velocity squared. The first computational model only accounted for the force of gravity on the ball. The net force on the ball can be calculated using Newton's second law. In this case, the net force is equal to the gravitational force, and the ball is considered to be in free fall. The net force was calculated to be 4.41 newtons, which is equal to the mass times the acceleration, since in this case, the acceleration is equal to the gravitational constant of 9.8 meters per second squared. The first computational model only accounted for the force of gravity on the ball. The net force on the ball can be calculated using Newton's second law. In this case, the net force is equal to the gravitational force, and the ball is considered in free fall. The net force was calculated to be 4.41 newtons, which is equal to the mass times the acceleration, since in this case, acceleration is equal to 9.8 meters per second squared. In order to create this model, I plugged in the mass of the ball and used the data collected from Tracker to determine the initial position and initial velocity of the ball. I plugged in negative 4.41 newtons as the net force. This value is negative since the ball is moving away from the origin towards the negative y direction. Since this model only accounted for the force of gravity, the ball from the computational model moved faster than the ball observed in real life. The second computational model accounts for the force of gravity and the turbulent drag. I had to change the VPython code to account for both of these things instead of only for gravity. Turbulent drag is equal to a constant times the velocity squared. The value I determined for b was 0.0521. In the code, I changed b equals 0 to say b equals 0.0521, so that when the model was run, it would account for the drag as well as the gravity. I calculated this value using the acceleration from the position versus time graph of the data from Tracker. The acceleration in this graph is equal to negative 4.33 meters per second squared, or the second derivative of the equation for the polynomial of best fit in the graph. The net force is equal to mass times the acceleration, so the net force with turbulent drag in the observed model is negative 1.949 newtons when Newton's second law is applied. The net force is equal to the drag force plus the gravitational force, so the drag force was determined to be 2.46 newtons. I then divided the drag force by the average velocity squared to obtain a value of b. This graph shows all of the previously described models' position versus time data. The blue line is the observed data from Tracker, the orange line is the model with drag, and the gray is the model with no drag. The observed model had the velocity with the largest magnitude, the model with no drag had the second largest velocity, and the model with drag had the slowest velocity. Terminal velocity is reached when the net force is 0 and the drag force is equal to the gravitational force. None of these models reached terminal velocity, although the observed model was beginning to approach it. If the object were initially thrown downward, it would take much longer to reach terminal velocity, since the force is in the negative y direction, but have a larger magnitude. Overall, this lab represented how Newton's second law is applied to moving objects that have a net force other than 0. In this case, the different forces acting on a falling object were represented using computational models and compared to a real-life example.